Okay, welcome back. In this video, we're going to discuss weak acids and weak bases, their properties, and then we'll go over how to get the pH of a weak acid in this video. In the next one, we'll do a weak base. So the thing to keep in mind about weak acids and weak bases is that they do not dissociate 100% into their ions. There's going to be an equilibrium or a reverse reaction that forces the ions back into the whole acid or whole base. So if you take a look at this first example right here of a weak acid, for instance, phosphoric acid, H3PO4, it is going to be in equilibrium with its ions H plus and then the H2PO4 1- ion. And it's going to have a small Ka value. Okay. Contrasting that with strong acids, which have a large Ka value, weak acids will have a small Ka value because they have this reverse reaction going on that forces the H plus and the H2PO4 back together into H3PO4. So in other words, weak acids and weak bases, they don't like to break apart, and they're not going to be totally reactive in that sense. The weak base is the same idea. It does not like to break apart into its separate ions, so a base like ammonium hydroxide here will have, again, that reverse reaction that's going to force the two ions to come back together. And as a result, the Kb, because it's a base, will be very small. Now, how do you get the pH of one of these? We'll start with the weak acid in this video, and the next video we'll do the weak base. But in order to find the pH of a weak acid, you're going to need to use those equilibrium Rice tables that we learned about in order to figure out how much of the acid actually went in or broke up into its ions. And then once you know what that is, you can take the negative log and get the pH. So let's take a look at this problem right here. What is the pH of a 0.30 molar methanoic acid HCOOH solution? The Ka is 1.8 times 10 to the negative fourth. Whenever you're doing these weak acid problems, you're going to need to know the Ka, and they'll have to provide it to you or give it to you directly in the question or give it to you on a chart. So again, a good practice is to always start by showing the acid breaking up. And because this is a weak acid, we should use a double-headed arrow. And for these organic acids like methanoic acid, it's usually going to be the H that's next to an O that will be lost. So usually they're pretty good about giving you the equation anyways. And then the methanoic anion. So it'll break up like this. Now, last time we could just take the negative log of this acid and get the pH, but because this is a weak acid, we have to take into account that it's in equilibrium. So we are going to need those helpful and or dreaded, depending on your perception, Rice tables. Reaction, initial change, and then equilibrium. So the initial concentration was 0.30 before any breaking up began, and then we had none of this in solution and then none of that in solution. Once the reaction started, we know that we're going to start losing some of the reactant and then forming products, so those are going to be pluses. How much did we make? We don't know, so we're going to call that X. And technically it should be 1x because the molar coefficient out in front is 1, but it's okay to leave those ones off. And it'll be the same for those other two. And then just like any equilibrium problem, you add up the columns to get the E row. So this is 0.30 minus x, 0.30 minus x. This is 0 plus x, which is just x, 0 plus x, which is just x. I would avoid putting the pluses in front of here like this so that you don't confuse it with addition when you put it into the equilibrium expression. So these are the concentrations at equilibrium right here. Now, because this is an acid-base problem, or a weak acid pH problem, we really only need one part of this. And the only part that we're concerned about is the H plus concentration here, which is equal to X. So once we know what X is, we can go ahead and take the negative log. But first we're going to need to write a K expression. Ka, because it's an acid, is equal to, just like we write any other equilibrium expression, the concentration of the products over the concentration of the reactants. Now that we have our K expression, it's just a matter of plugging it in. And now at this point, if we try to solve the way it is, we will end up with a quadratic, and we want to try to avoid those. The AP exam is pretty good at not giving you quadratics. So because this K value is pretty small, times 10 to the negative fourth, or smaller, we can assume that the value of X is going to be small as well. So we will write assume small x. And remember, when you are going to make that small x assumption, you can only assume the x is small for anything that's attached by addition or subtraction. If it's attached by multiplication, you can't cross that x out. So we can only cross this bottom x. The two up top need to be left alone because they're multiplication. And then I like to rewrite the equation again without that x there. I'm going to combine those two x's up top to become x squared over 0.30, and this makes our lives so much easier. Now when we solve for x, we'll do that algebraically by multiplying both sides by that 0.30 and then taking the square root. And when we do that, we get 0.0073 to 2 sig figs molar. Now at this point you should technically do a check your assumption, or an assumption check, and so, which is also known as the percent ionization. And the way we do that is we'll take the concentration that we calculated of the acid divided by the original concentration, which was 0.30, multiply that by 100. If that is less, or 100%, if that is less than 5%, then our assumption is good. And in this case it will be. Yeah, so it's about 2.4% ionized. Basically what this means is that only 2.4% of this is going to ionize. That's less than 5%, so we're pretty good there. We can accept this assumption. And that is equal to the concentration of H+. Okay, since X is H+. Now that we know what the concentration of H+ is, we can now take the negative log of that answer there. pH is equal to the negative log of 0.0073 and then we got a pH of 2.14, or 2 sig figs. And so that's how you get the pH of a weak acid, ladies and gents. You do have to go through that dreaded step of the equilibrium table, the Rice table, because there is this reverse reaction going on. So we cannot definitively say that the concentration of the original acid is going to be equal and exact to the concentration of H+. As clearly you can see, if we assumed that, if we assume that it was behaving like a strong acid, then the concentration of H+ would be 0.30, and it is in fact not. The concentration of H+ was 0.0073, much less than what the original was. And if you were to take the negative log of that, you would have gotten a completely different and incorrect answer. So go ahead and try the practice problem on the Nearpod that follows this, and then in the video after this we'll be finding the pH of a weak base. It's essentially the same process up here, but we'll be finding the concentration of OH-, so we'll need to use that pH plus POH is equal to 14 to get the pH.